What if a single nuclear bomb could knock out every satellite orbiting Earth and paint the sky with an aurora visible across an entire ocean? Not as science fiction, but as something that already happened, documented in classified government files. On a warm July night in 1962. On that night, the United States military detonated a thermonuclear warhead 250 miles above the Pacific Ocean. And the consequences were so bizarre, so far beyond any prediction, that they rewrote the rules of warfare, space policy, and international law forever. The flash turned midnight into noon across Hawaii. Streetlights died from an invisible electromagnetic surge, and a ghostly red glow hung over the horizon for more than an hour. Satellites launched at tremendous cost began failing, one after another, over the following months. The event remains one of the most extraordinary and most underappreciated moments in the history of nuclear weapons. But to fully understand what happened that night, and what would happen if we tried it again, or if nature did something far worse, we need to start with the physics that makes it all possible. The fundamental mechanism of nuclear explosions. The difference between splitting atoms and fusing them, and why space changes absolutely everything about how that energy behaves. Nuclear explosions come in two fundamental varieties, and the distinction matters enormously when you are trying to understand what happens when one goes off beyond the atmosphere. The first type is nuclear fission. Fission occurs when a heavy, unstable atomic nucleus, typically uranium-235 or plutonium-239, absorbs a neutron and splits into two or more lighter nuclei. When the atom breaks apart, it releases energy because the total mass of the resulting fragments is slightly less than the mass of the original nucleus plus the incoming neutron. That tiny difference in mass is converted directly into energy according to Einstein's famous equation, E equals mc squared. The amount of energy is staggering relative to the amount of matter involved. A single kilogram of uranium-235, if entirely fissioned, would release roughly the same energy as detonating 17,000 tons of TNT. In practice, weapons do not achieve perfect efficiency, but even partial fission of a few kilograms of material can level a city. The key to making a fission weapon work is the chain reaction. When a uranium-235 nucleus splits, it releases 2 or 3 fast neutrons along with the energy. Those neutrons can then strike other uranium nuclei, causing them to split as well, releasing still more neutrons. If enough fissile material is assembled in the right geometry, a quantity known as a critical mass, the chain reaction becomes self-sustaining and accelerates exponentially. Within a few millionths of a second, an astronomical number of atoms have split, and the total energy released is enough to produce temperatures of tens of millions of degrees and pressures of millions of atmospheres. The bomb that was dropped on Hiroshima in August 1945, codenamed Little Boy, used about 64 kilograms of highly enriched uranium and produced an explosion equivalent to roughly 15,000 tons of TNT, or 15 kilotons. It killed an estimated 70,000 to 80,000 people instantly and leveled nearly 5 square miles of the city. The second bomb, Fat Man, dropped on Nagasaki 3 days later, used plutonium-239 and produced a yield of about 21 kilotons. These were fission weapons, first-generation nuclear bombs, and they represent the baseline, against which all subsequent nuclear devices are measured. The second type of nuclear explosion is fusion, and it operates on the opposite principle. Instead of splitting heavy atoms apart, fusion forces light atoms together. Specifically, isotopes of hydrogen, deuterium and tritium, are compressed and heated until their nuclei overcome their mutual electrical repulsion and merge to form helium. This process also converts a small fraction of the total mass into energy, but the energy per unit mass is even greater than for fission. Fusion is what powers every star in the universe, including our own sun. At the sun's core, where temperatures reach about 27 million degrees Fahrenheit and pressures are roughly 250 billion atmospheres, approximately 600 million tons of hydrogen are converted into helium every single second. In that process, about 4 million tons of matter are transformed into pure energy each second, energy that eventually reaches Earth as sunlight and warmth. Fusion weapons, commonly called hydrogen bombs or thermonuclear weapons, harness this stellar process in a two-stage design. The first stage is a fission bomb, a conventional atomic bomb, which serves as the trigger. When the fission bomb detonates, it produces the extreme temperatures and pressures needed to ignite the second stage. A capsule of fusion fuel, typically lithium deuteride. The X-rays from the fission primary compress and heat the fusion secondary until thermonuclear. Reactions begin. The result is an explosion that can be hundreds or thousands of times more powerful than a pure fission weapon. The most powerful nuclear weapon ever detonated was the Soviet Union's Tsar Bomba. Tested on October 30, 1961, over the Novaya Zemlya archipelago in the Arctic Ocean. The original design had a yield of approximately 100 megatons of TNT, but it was intentionally scaled down to about 50 megatons, roughly 50 million tons of TNT equivalent, to reduce fallout. Even at half power, the Tsar Bomba was more than 3,300 times as powerful as the Hiroshima bomb. The fireball reached a diameter of nearly 5 miles. The mushroom cloud rose to an altitude of about 40 miles, well into the stratosphere. The shockwave circled the Earth 3 times. Windows were broken 560 miles from ground zero. The flash was visible at a distance of over 600 miles. It remains, by a wide margin, the single most energetic event ever deliberately caused by human beings. And yet, as we will see, it is a firecracker compared to what the universe routinely produces. To put these numbers in context, consider the energy scales involved. 1 ton of TNT, when detonated, releases approximately 4.2 billion joules of energy, or about 1.2 megawatt hours. The Hiroshima bomb released roughly 63 trillion joules. The Tsar Bomba released roughly 210 quadrillion joules, or 210 petajoules. Meanwhile, the Sun outputs approximately 384.6 yottawatts, that is, 384.6 septillion watts continuously. In a single second, the Sun radiates more energy than the entire Tsar Bomba arsenal could produce, even if you detonated one every second for 30 million years. Human nuclear weapons, for all their terrifying destructive power, operate on a scale that is cosmically insignificant. This perspective becomes crucial when we begin discussing what nuclear explosions look like in space, where the energy has no atmosphere to interact with and must propagate purely as radiation, and where natural phenomena like solar flares and supernovae dwarf anything humanity could conceivably create. When a nuclear weapon detonates within Earth's atmosphere, the energy distributes itself across several destructive mechanisms that work in concert. Understanding these effects on the ground is essential because each one changes dramatically, or vanishes entirely, when the detonation occurs in the vacuum of space. The first and most immediately lethal effect is the thermal pulse. Within a few millionths of a second of detonation, the weapon's core reaches temperatures comparable to the interior of the Sun, tens of millions of degrees. This superheated material radiates enormous quantities of energy as visible light, infrared radiation, and ultraviolet radiation, creating a fireball that expands rapidly as it heats the surrounding air. For a weapon in the megaton range, the fireball can reach a diameter of several miles and remain luminous for several seconds. The thermal radiation from this fireball can cause third-degree burns to exposed skin at distances of 10 miles or more, depending on yield and atmospheric conditions. In Hiroshima, the thermal pulse ignited fires across a radius of roughly 1.2 miles from ground zero and caused severe burns at distances up to 2 miles. The heat was intense enough to leave permanent shadows on concrete walls, where objects or people had partially shielded the surface from the flash. Following the thermal pulse, the second major effect is the blast wave, or overpressure. The fireball's extreme heat causes the air around it to expand at tremendous speed, creating a spherical shock front, a wall of compressed air that moves outward faster than the speed of sound. Immediately behind the shock front is a region of intense dynamic pressure, essentially a hurricane-force wind that can reach speeds of several hundred miles per hour near the detonation point. For a 1 megaton weapon detonated at optimal altitude, the blast overpressure is sufficient to destroy reinforced concrete buildings at a radius of about 2.5 miles and to inflict fatal injuries on unprotected humans at roughly 4 miles. Beyond the direct shock front, the blast also creates a negative pressure phase as the superheated air rushes back toward the partial vacuum left in the fireball's wake, generating powerful reverse winds. In Hiroshima, the blast wave demolished virtually every structure within a mile of ground zero and caused severe damage out to about 2 miles. The combined thermal and blast effects are responsible for the majority of casualties in a nuclear attack on a city. The third major effect is ionizing radiation. Nuclear detonations produce intense bursts of gamma rays and neutrons in the first microsecond, known as the initial or prompt radiation. For smaller weapons, this prompt radiation can be a significant cause of casualties because the lethal radius from radiation may extend beyond the lethal radius of blast and thermal effects. For larger weapons in the megaton range, however, the blast and heat kill zones generally extend farther than the prompt radiation zone. So radiation is proportionally less important as an immediate cause of death, but remains devastating in other ways. After the initial burst, the longer-term radiation hazard comes from radioactive fallout, the remains of the weapon materials and irradiated debris that are carried aloft in the mushroom cloud and then settle back to Earth over hours, days, and weeks, depending on the weapon design and the height of burst. Fallout can contaminate thousands of square miles with radioactive isotopes such as strontium-90, cesium-137, and iodine-131, which can cause acute radiation syndrome, cancer, and birth defects in exposed populations. The survivors of Hiroshima and Nagasaki, known as hibakusha, have experienced elevated rates of leukemia, thyroid cancer, and other radiation-related diseases for decades after the bombings. The fourth and perhaps most visually iconic effect of an atmospheric nuclear detonation is the mushroom cloud. This is not merely an aesthetic phenomenon. It is a direct consequence of the physics involved. The fireball, being extremely hot, is also extremely buoyant relative to the surrounding air. It rises rapidly, like a colossal hot air balloon, at speeds that can exceed 300 miles per hour in the initial seconds. As it ascends, it pulls a column of dust, debris, and smoke upward in its wake, forming the mushroom's stem. When the fireball reaches the tropopause, the boundary between the troposphere and the stratosphere, at roughly 7 to 12 miles altitude depending on latitude, it encounters a temperature inversion that inhibits further vertical growth. The fireball spreads laterally, forming the mushroom's cap. For very large weapons, the fireball can punch through the tropopause entirely and reach altitudes of 25 miles or more in the stratosphere. The mushroom cloud from the Tsar Bomba reached approximately 40 miles in altitude, with a cap roughly 60 miles wide. The cloud persists for hours, gradually dispersing while carrying radioactive particles that eventually settle as fallout. This mushroom cloud formation is entirely dependent on the presence of an atmosphere, specifically on the existence of buoyant convection driven by temperature differences in a gravitational field with a gas medium. Remove the atmosphere, and this dramatic visual signature disappears completely. The fifth critical effect, one that has gained increasing strategic importance in the modern era, is the electromagnetic pulse, known by its abbreviation EMP. When a nuclear weapon detonates, its initial burst of gamma rays interacts with the surrounding air molecules, stripping electrons from their atoms through a process called the Compton effect. These high-energy electrons spiral along Earth's magnetic field lines, producing a brief but extraordinarily intense pulse of electromagnetic energy across a wide spectrum of radio frequencies. For a surface-level or low-altitude detonation, the EMP affects a relatively localized area. But for a high-altitude detonation, one occurring above the atmosphere, the geometry changes dramatically. The gamma rays can travel unimpeded for hundreds of miles before they strike the upper atmosphere, where they generate Compton electrons over an enormous area. The resulting EMP can blanket entire continental regions in a single pulse. The electromagnetic fields induced in long conductors, power lines, telephone cables, antennas, pipelines, can produce voltage spikes capable of destroying unshielded electronic equipment, burning out transformers, and disrupting communication networks across thousands of miles. Modern military and strategic planners consider a single high-altitude nuclear detonation to be one of the most efficient ways to cripple a technologically advanced nation's infrastructure without causing direct physical destruction or casualties on the ground. The vulnerability of modern electronic systems, computer chips, telecommunications networks, the electrical grid, financial systems, makes EMP a uniquely dangerous 21st century threat. Now strip away the atmosphere entirely. Remove the air, the moisture, the gas molecules, the medium through which shock waves propagate and mushroom clouds form. You are in space, true vacuum, or as close to it as nature provides, and you detonate a nuclear weapon. What happens? The first and most profound difference is the absence of a blast wave. On Earth, roughly half of a nuclear weapon's energy is delivered as blast, the physical shock wave that demolishes buildings, shatters windows, and crushes human bodies. This blast effect is entirely a consequence of the weapon's energy being deposited into the surrounding air, which is then accelerated outward as a wave of compressed gas. In space, there is no air. There is nothing to compress, nothing to push, nothing to carry a shock front. The nuclear device still releases exactly the same amount of energy, but that energy has no gaseous medium to transfer into. The weapon's casing, tamper, and structural materials are vaporized into a rapidly expanding plasma cloud. But this cloud disperses into the vacuum almost instantly, losing its coherence within microseconds. There is no sustained pressure wave, no hurricane-force wind, no overpressure capable of collapsing a building. If you placed a structure a few hundred feet from the detonation point in space, it would be hit by thermal radiation and a brief spray of vaporized weapon debris. But it would not experience anything resembling the devastating blast wave that levels cities on Earth. This means that the most destructive mechanism of terrestrial nuclear weapons simply does not exist in the vacuum of space. The second difference involves the fireball. On Earth, the fireball is a sustained, luminous sphere of superheated air that persists for several seconds, growing and cooling as it radiates. In space, there is no air to heat and hold in a glowing ball. The weapon materials themselves become a plasma at millions of degrees. And this plasma does emit intense light, but it expands freely in all directions at enormous speed, cooling rapidly as it does so. The visible flash is extremely brief, perhaps a fraction of a second, before the expanding plasma becomes too diffuse and cool to emit significant visible light. An observer at a safe distance would see an incredibly bright point of light flare up and then vanish almost instantaneously, a cosmic flashbulb going off in the darkness. There would be no lingering fireball, no roiling mass of incandescent gas, no slowly rising column of fire. Just a burst and then darkness again, and there would be absolute silence. Sound requires a medium to travel through, and space provides none. The detonation would be the most powerful silent event imaginable. The third difference involves the radiation environment. On Earth, the atmosphere absorbs a significant fraction of the gamma rays, X-rays, and neutrons produced by a nuclear detonation. The air acts as a shield, attenuating these radiation types over distance. A person standing 2 miles from a low-yield detonation in atmosphere might receive a survivable dose of prompt radiation, partly because the air between them and the blast has absorbed and scattered much of it. In space, there is no such shielding. Gamma rays, X-rays, and neutrons travel outward at or near the speed of light, completely unattenuated by any intervening medium, and their intensity decreases only with the inverse square of the distance. A nuclear detonation in space would irradiate everything within line of sight with the full, unshielded output of prompt radiation. Satellites, spacecraft, and astronauts hundreds of miles away could receive lethal or damaging doses. The radiation environment in space after a nuclear detonation is, in a very real sense, more dangerous over long distances than it is on Earth, precisely because there is nothing to stop it. The fourth difference is the absence of the mushroom cloud. Without an atmosphere, there is no buoyant convection, no rising column of heated gas, no cap of spreading debris. The expanding plasma simply flies outward in a roughly spherical shell and dissipates. Any weapon debris, vaporized metals, fission products, continues outward indefinitely or until it encounters something, be it a spacecraft, a planet's atmosphere, or the solar wind. There is nothing to pull the debris back, nothing to create the organized structure of a mushroom cloud. The visual signature of a nuclear explosion in space is utterly unlike anything we associate with nuclear weapons on Earth. So if there is no blast, no sustained fireball, no mushroom cloud, and no sound, does a nuclear explosion in space matter? The answer is an emphatic yes, and the proof lies in what happened on July 9, 1962. When the United States conducted a test codenamed Starfish Prime, the largest nuclear detonation ever carried out in outer space. The test was part of Operation Fishbowl, itself a subset of the larger Operation Dominic series of nuclear tests conducted in 1962. The geopolitical context was the Cold War. The Soviet Union had broken a 3-year voluntary moratorium on nuclear testing in September 1961 by conducting a series of atmospheric tests that included the Tsar Bomba. The United States responded with its own accelerated testing program, and Starfish Prime was among the most ambitious experiments planned. The weapon was a W-49 thermonuclear warhead with a yield of 1.4 megatons, roughly 93 times the power of the Hiroshima bomb. It was mounted on a Thor intermediate-range ballistic missile and launched from Johnston Atoll, a small island in the central Pacific Ocean, about 900 miles west-southwest of Honolulu, Hawaii. The missile carried the warhead to an altitude of 250 miles, approximately 400 kilometers, which placed it well above the atmosphere, in what is functionally outer space. For reference, the International Space Station orbits at roughly the same altitude. The detonation occurred at 11:00 p.m. local Hawaii time, meaning the Hawaiian Islands were in darkness, providing an ideal backdrop against which to observe the effects. What happened next exceeded every prediction. The initial flash was visible from Hawaii, 900 miles away, as a brilliant white point of light that appeared on the horizon and briefly turned the night sky as bright as day, even through heavy cloud cover. Observers in Honolulu reported that the sky momentarily lit up with an intensity that rivaled high noon. Photographers captured the flash cutting through layers of cloud with an eerie, diffuse glow. But the truly astonishing effects came in the seconds and minutes that followed. The nuclear detonation released an enormous burst of gamma rays, which, traveling unimpeded through the vacuum of space, struck the upper atmosphere over a vast area. As these gamma rays interacted with air molecules at the top of the atmosphere, they stripped electrons from atoms on a massive scale. These energetic electrons, guided by Earth's magnetic field, spiraled along field lines and excited atmospheric gases in exactly the same way that charged particles from the solar wind create natural auroras. The result was a spectacular artificial aurora, a man-made northern lights display that lit up the sky in vivid colors of red, white, and purple across a huge swath of the Pacific. At Johnston Atoll, directly below the detonation, observers described a mottled red disk that covered the sky from nearly horizon to horizon, with white-yellow streaks extending along the north-south magnetic field line. At Kwajalein Atoll, 400 nautical miles to the west, observers watched in astonishment as the sky turned through a sequence of colors, brilliant white, expanding green, then concentric rings of light that raced overhead and froze in place, followed by a deep, dull burning red glow that covered the entire eastern sky and persisted for more than 90 minutes, interspersed with tremendous white rainbow-like arcs. The display was visible to the naked eye from multiple Pacific islands and was even observed in New Zealand, more than 4,000 miles from the detonation point. At Christchurch, New Zealand, observers recorded white auroral shafts emanating from the magnetic zenith within 10 seconds of the explosion, followed by a red glow that covered most of the sky and remained visible for about 12 minutes, with photometric instruments recording elevated light levels for more than an hour. This was completely unprecedented. The aurora was artificial, generated not by the solar wind, but by a human-made nuclear explosion, and it demonstrated that a detonation in space could have dramatic visible effects over an area spanning thousands of miles. But the visible aurora was only one of several extraordinary consequences. The electromagnetic pulse generated by Starfish Prime was, according to official reports, far larger than expected, so much larger that it drove many of the scientific instruments off scale, making accurate measurement impossible. The EMP propagated outward and downward, inducing powerful electrical currents in conductors across the Hawaiian Islands, 900 miles away. In Honolulu, approximately 300 streetlights were knocked out simultaneously. Burglar alarms across the city were triggered. A microwave telecommunications link operated by the telephone company was burned out, cutting telephone service from the island of Kauai to the rest of Hawaii. At the time, electronic infrastructure in Hawaii was relatively simple compared to today's systems. There were no computer networks, no internet, no semiconductor-based grid control systems. The damage was therefore limited. But military analysts and scientists immediately recognized the terrifying implication. A single high-altitude nuclear detonation could, in principle, disable the electronic infrastructure of an entire nation. In a modern context, with society's near-total dependence on electronics for power distribution, communications, transportation, finance, water treatment, and medical care, the consequences of a Starfish Prime scale EMP over a major continental landmass would be catastrophic on a scale that is difficult to overstate. Perhaps the most consequential and longest-lasting effect of Starfish Prime was one that was not fully anticipated: the creation of an artificial radiation belt around the Earth. The nuclear explosion released approximately 10 to the 29th power high-energy electrons into the magnetosphere. While some of these electrons followed magnetic field lines down into the atmosphere, producing the auroral displays, others became trapped in the Earth's magnetic field, forming a persistent belt of artificial radiation that encircled the planet. This artificial radiation belt significantly enhanced the intensity of the natural inner Van Allen radiation belt, increasing electron densities by several orders of magnitude. The consequences for the nascent space age were immediate and devastating. In the months following Starfish Prime, at least 6 satellites suffered severe damage or complete failure as a result of the enhanced radiation environment. Among the casualties were Telstar-1, the world's first commercial communications satellite, launched by AT&T just one day after the Starfish Prime detonation, and Ariel-1, the United Kingdom's first satellite. Telstar-1, designed to relay television signals and telephone calls across the Atlantic, began experiencing intermittent failures in its transistorized electronics within months of launch, and its degradation was directly attributed to radiation damage from the Starfish Prime artificial radiation belt. Ariel-1, a joint U.S.-British scientific satellite, suffered damage to its solar panels and had its timer system disabled. Other satellites affected included the TRAC and Transit 4B navigation satellites. The artificial radiation belt created by the single 1.4 megaton explosion persisted for years. Some energetic electrons were still detectable 5 years after the test, and it demonstrated that a nuclear detonation in space could render entire orbital regimes hazardous or unusable. In 1962, there were only a handful of satellites in orbit. Today, there are thousands, and modern civilization depends on them for GPS navigation, weather forecasting, military surveillance, telecommunications, internet connectivity, and scientific research. A Starfish Prime-scale detonation today could potentially disable or destroy a substantial fraction of the world's satellite infrastructure, with cascading consequences for the global economy and military capabilities. The shock of Starfish Prime reverberated through the political and diplomatic world. Scientists and military planners who had advocated for space-based nuclear testing suddenly confronted the reality that such tests could damage their own nation's space assets as readily as an adversaries. The realization that nuclear explosions in space could create long-lasting radiation hazards to all spacefaring nations, regardless of who detonated the weapon, provided powerful motivation for arms control. In 1963, the United States, the United Kingdom, and the Soviet Union signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons testing in the atmosphere, in outer space, and underwater. Only underground testing was still permitted. Subsequently, the Outer Space Treaty of 1967 explicitly prohibited the placement of nuclear weapons in orbit around the Earth, on the Moon, or on any other celestial body, and banned nuclear detonations in space. These treaties have been respected by the major spacefaring nations for over 6 decades, and Starfish Prime remains the last nuclear detonation conducted in outer space. It stands as both a warning and a precedent, proof that the consequences of nuclear weapons in space extend far beyond the immediate vicinity of the explosion and can affect the entire planet. To appreciate the full scale of explosive energy in the cosmos, it is worth turning our attention to the nearest star. The Sun, which appears as a gentle, life-giving disk in our daytime sky, is in fact a continuously operating thermonuclear furnace of almost incomprehensible power. At its core, where temperatures reach approximately 27 million degrees Fahrenheit and pressures exceed 250 billion atmospheres, hydrogen nuclei are fused into helium at a rate of roughly 620 million metric tons per second. In each second of this process, about 4.26 million metric tons of matter are converted into energy that radiates outward through the Sun's layers and eventually streams into space as sunlight, heat, and a whole spectrum of electromagnetic radiation. The Sun's luminosity, its total power output, is approximately 3.846 times 10 to the 26th watts. To put this in the terms we have been using, the Sun's energy output in a single second is equivalent to approximately 91.6 billion megatons of TNT. That means the Sun produces, every second, the energy equivalent of roughly 1.8 billion tsar bombas detonating simultaneously. The entire nuclear arsenal of the United States, estimated at its Cold War peak at roughly 25,000 warheads with a combined yield of perhaps 10,000 megatons, could detonate all at once and still represent less than 1/10,000th of the Sun's output in a single second. The Sun has been doing this continuously for approximately 4.6 billion years and is expected to continue for another 5 billion years before exhausting its hydrogen fuel. It is the ultimate demonstration that nuclear fusion, when operating on a stellar scale, produces energy on a level that makes human nuclear weapons look trivial. But the Sun does not always radiate smoothly. Periodically, it produces violent outbursts called solar flares, sudden, intense brightenings that occur in the vicinity of sunspot groups on the Sun's surface. Solar flares are caused by the sudden release of magnetic energy that is built up in the solar atmosphere. When the complex, twisted magnetic field lines in an active region reconnect and reorganize, they release energy in the form of electromagnetic radiation across the entire spectrum, radio waves, visible light, ultraviolet, X-rays, and gamma rays, as well as energetic particles. The energy released by a major solar flare can be equivalent to millions of tsar bombas detonating simultaneously. X-class flares, the most powerful category, occur roughly 10 times per year during the peak of the 11-year solar cycle. They can release energy on the order of 10 to the 25th joules in a matter of minutes, roughly the total energy output of the entire world's electrical generation capacity for 100,000 years, released in a single burst. Even more dramatic are coronal mass ejections, or CMEs, which often accompany solar flares. A CME is a massive eruption of solar plasma and magnetic field from the Sun's corona into interplanetary space. A large CME can eject billions of tons of magnetized plasma at speeds of up to 2,000 miles per second, carrying with it a powerful magnetic field. When a CME impacts Earth's magnetosphere, it compresses the magnetic field, injects energetic particles, and can trigger geomagnetic storms that affect the entire planet. The most powerful solar storm in recorded history was the Carrington event of September 1859. On September 1st of that year, the English astronomer Richard Carrington, while observing sunspots, witnessed an intense white light solar flare, the first such flare ever directly observed. Within hours, Earth was struck by a massive CME. The resulting geomagnetic storm was extraordinary. Auroras, normally visible only in high-latitude regions near the Arctic and Antarctic, were seen as far south as the Caribbean, Colombia, and Hawaii, and as far north as Queensland, Australia. The entire night sky in many locations glowed so brightly that people could read newspapers by the auroral light. Telegraph systems across North America and Europe failed catastrophically. Operators received electric shocks from their equipment. Some telegraph lines caught fire. In several documented cases, telegraph operators disconnected their batteries and found that the geomagnetically induced currents were strong enough to continue transmitting messages using the aurora's electricity alone. The Carrington event is estimated to have released energy equivalent to approximately 10 billion megaton of TNT, making it roughly 200 million times more energetic than the Tsar Bomba. In 1989, a far milder solar storm, caused by a CME that struck Earth on March 13th, induced currents in Hydro-Quebec's power transmission system that tripped protective relays and caused a cascading failure. The entire province of Quebec, home to roughly 6 million people at the time, lost electrical power for 9 hours. Transformers were damaged as far away as New Jersey. The 1989 event was perhaps 1/10 the intensity of the Carrington event. A Carrington-scale event today, with modern civilization's near-total dependence on electronics, satellite systems, and interconnected power grids, could cause trillions of dollars in damage and take years to fully repair. In 2012, a Carrington-class CME narrowly missed Earth by approximately 9 days of orbital separation, a miss that was not widely reported at the time, but was later described by NASA scientists as a near miss of potentially catastrophic proportions. A 2013 study by Lloyds of London and the Atmospheric and Environmental Research Group estimated that a Carrington-scale event could cause 60 cents to $2.60 trillion in damage to the United States alone, with recovery taking 4 to 10 years for the hardest-hit regions. These solar phenomena, flares, CMEs, geomagnetic storms, are in a very real sense natural nuclear explosions on a scale that renders human weapons infinitesimal. They demonstrate that the physics of nuclear fusion, which we have harnessed only in its most crude and destructive form in hydrogen bombs, operates throughout the cosmos at energy levels that beggar human imagination. Every star is a fusion reactor. Every stellar flare is a nuclear detonation. The universe runs on nuclear energy, and has done so for 13.8 billion years. Now let us consider what might happen at the most extreme gravitational environment known to physics, the vicinity of a black hole. This is admittedly a thought experiment. No one is going to detonate a nuclear weapon near a black hole anytime soon, but it illuminates fundamental aspects of how energy behaves under conditions of extreme spacetime curvature. And it connects our discussion of nuclear explosions to some of the deepest questions in modern physics. A black hole is what remains when a massive star, typically one with at least 20 to 25 times the mass of the Sun, exhausts its nuclear fuel and collapses under its own gravity. The collapse compresses the stellar core into a point of essentially infinite density called a singularity, surrounded by a boundary known as the event horizon. The event horizon is not a physical surface but a mathematical boundary, the radius at which the escape velocity equals the speed of light. Nothing that crosses the event horizon, not matter, not light, not information, can ever return to the outside universe, at least according to classical general relativity. The gravity near a black hole is so intense that it warps the fabric of spacetime itself, producing effects that are directly observable and have been confirmed by experiments and astronomical observations. If you detonated a nuclear weapon in the vicinity of a black hole, say, a few hundred miles outside the event horizon of a stellar mass black hole, several remarkable things would happen. First, the explosion would still occur normally from the perspective of someone located right next to the bomb. The physics of nuclear fission and fusion do not depend on the gravitational environment. The chain reaction would proceed, the energy would be released, and the fireball would form. However, an observer watching from a safe distance, far from the black hole's gravitational influence, would see something profoundly different. Due to gravitational time dilation, a prediction of Einstein's general theory of relativity that has been confirmed by precision measurements using atomic clocks on GPS satellites and by observations of stars orbiting the supermassive black hole at the center of our galaxy. Time passes more slowly in stronger gravitational fields. Near a black hole, this effect becomes extreme. The distant observer would see the nuclear explosion unfold in apparent slow motion. as if time near the black hole had been stretched like taffy. The flash of light would appear to linger, drawn out over a much longer period than the explosion actually lasted in its local reference frame. Furthermore, the light from the explosion would be gravitationally redshifted. Its wavelength would be stretched by the black hole's gravity as it climbs out of the gravitational well, shifting it toward the red end of the spectrum and reducing its energy. A brilliant white flash in the local frame might appear as a dim, reddish glow to the distant observer. If the detonation occurred close enough to the event horizon, the redshift would be so severe that the light would effectively fade to nothing before reaching the observer, as if the explosion had been swallowed by the darkness itself. And indeed, any portion of the explosion's energy, whether light, radiation, or physical debris, that crossed the event horizon would be permanently lost to the outside universe. The black hole would simply absorb it, adding infinitesimally to its own mass and energy. According to the no-hair theorem of classical general relativity, a black hole is characterized by only three properties: its mass, its electric charge, and its angular momentum. All other information about what fell in, whether it was a nuclear bomb, a grand piano, or a library, is lost, at least from the perspective of external observers. This leads to the famous black hole information paradox, a deep unresolved problem in theoretical physics that pits general relativity against quantum mechanics. Stephen Hawking, in 1974, showed theoretically that black holes are not perfectly black. They emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation causes the black hole to very slowly lose mass and energy, a process called black hole evaporation. For stellar mass black holes, the rate of Hawking radiation is negligibly small. The black hole absorbs far more energy from the cosmic microwave background than it emits, and evaporation would take far longer than the current age of the universe. But for very small, hypothetical black holes with masses on the order of a mountain or less, Hawking radiation would be significant. As such a black hole radiates away its mass, it gets hotter, which causes it to radiate faster, which causes it to get hotter still, in a runaway process that culminates in a final burst of radiation, a black hole explosion. The energy released in this final burst would be considerable. A black hole with the mass of an automobile, for instance, would release roughly the energy equivalent of a large nuclear weapon in the final fraction of a second of its evaporation. No such event has ever been observed, and it remains unclear whether primordial black holes of the right mass exist in the universe. But the theoretical prediction stands as one of the most remarkable implications of combining quantum mechanics with general relativity. Another fascinating aspect of a nuclear detonation near a black hole would be the gravitational lensing of the explosion's light. Black holes bend the paths of light rays that pass near them, acting as gravitational lenses. If the explosion occurred behind the black hole from an observer's perspective, the observer might see the explosion's light bent around the black hole, arriving from multiple directions simultaneously, or forming an Einstein ring, a circle of light caused by the perfect alignment of source, lens, and observer. The distorted, multiplied images of the explosion would create a visual spectacle that has no parallel in terrestrial experience. In some configurations, the observer might even see the light from the explosion circling the black hole one or more times before escaping, creating delayed echoes of the flash arriving at progressively later times. These effects are not speculation. Gravitational lensing has been observed in numerous astronomical contexts, from galaxy clusters bending the light of more distant galaxies to the direct imaging of the photon ring around the supermassive black hole M87 star by the Event Horizon Telescope in 2019. Massive black holes at the centers of galaxies are also associated with some of the most energetic phenomena in the known universe. When matter falls into these supermassive black holes, which can contain billions of solar masses, it forms a swirling accretion disk that heats up to millions of degrees, radiating prodigious amounts of X-rays and other high-energy radiation. In some cases, the black hole launches jets of relativistic plasma, streams of matter moving at nearly the speed of light, from its polar regions, extending thousands or even millions of light years into intergalactic space. These jets carry more energy than entire galaxies. A nuclear bomb detonated in the vicinity of such a system would be less than a grain of sand thrown into a furnace, utterly insignificant against the backdrop of energies that routinely operate near supermassive black holes. The accretion disk of a typical active galactic nucleus radiates power on the order of 10 to the 39th watts, roughly 1 trillion times the luminosity of the sun. No human-made device could make the slightest measurable impression on such a system, having explored the destructive potential of nuclear explosions in space. It is worth examining one of the most audacious proposals ever made for putting that energy to constructive use: using nuclear bombs to propel a spacecraft. This was the core idea behind Project Orion, a study conducted from the late 1950s through 1965 by the United States Air Force, DARPA, and NASA, headquartered at General Atomics in San Diego, California. The project was led by physicist Ted Taylor, one of the most brilliant nuclear weapon designers of his generation, and included Freeman Dyson, the legendary theoretical physicist from the Institute for Advanced Study in Princeton, New Jersey, who took a leave of absence from academia to work on what he considered the most exciting engineering project of the 20th century. The concept was straightforward in principle, even if staggering in its ambition. A large spacecraft would carry a magazine of small nuclear bombs, thousands of them, one at a time. These bombs would be ejected through a hole in the center of a massive steel pusher plate mounted at the rear of the ship. Each bomb would detonate about 65 to 100 feet behind the plate, and the blast of plasma and radiation would slam into the pusher plate, giving the ship a powerful kick. Shock absorbers, a sophisticated two-stage system of mechanical springs and gas pistons, would smooth out the individual impulses into a continuous acceleration tolerable for the crew. The bombs would be detonated at a rate of roughly 1 per second, each adding a velocity increment of about 30 meters per second, producing a sustained acceleration of approximately 1 g, comfortable enough for a human crew to live and work in what would feel like normal Earth gravity. The nuclear pulse drive had two enormous advantages over any other propulsion system, then or now. First, it combined extremely high exhaust velocity, the speed at which propellant leaves the engine, a key measure of efficiency, with extremely high thrust. Chemical rockets like the Saturn V produce high thrust but relatively low exhaust velocity, meaning they burn through enormous quantities of propellant quickly. Ion engines produce very high exhaust velocity but minuscule thrust, meaning they take months or years to build up speed. The Orion drive uniquely could do both. It could accelerate a massive ship rapidly. Freeman Dyson calculated that the exhaust velocity of the nuclear pulse units would be in the range of 19 to 31 kilometers per second for interplanetary designs, roughly 10 times that of the best chemical rockets, while simultaneously producing meganewtons of thrust. The implications were extraordinary. NASA produced a detailed mission profile for a Mars round trip using a 4,000-ton Orion vehicle. 125 days total, carrying 8 astronauts. With a payload capacity to Mars orbit and return of roughly 800 tons, compared to the approximately 2 tons that the Saturn V could soft land on the Moon. The larger designs were even more ambitious. A 10,000-ton advanced interplanetary Orion could have carried 300 tons of payload to Mars orbit and back, or 300 tons to Saturn and back in a 3-year mission. A conceptual Super Orion, with a mass of 8 million tons and a diameter of 400 meters, was envisioned as an interstellar ark, a self-contained city ship that could carry thousands of people to nearby star systems. Freeman Dyson, in a 1968 paper titled Interstellar Transport, published in Physics Today, analyzed the theoretical maximum performance of nuclear pulse propulsion for interstellar flight, using fusion bombs rather than fission. He calculated that a momentum-limited Orion starship could achieve velocities of up to 10,000 kilometers per second, roughly 3.3% of the speed of light, which would allow it to reach Alpha Centauri, the nearest star system, at 4.37 light-years distance, in approximately 133 years. Later analyses suggested that an optimized fission-powered Orion could reach 9 to 11% of the speed of light. while fusion-powered designs might achieve even higher velocities. The astronomer Carl Sagan suggested, with characteristic wit and vision, that this would be an excellent use for the world's stockpiles of nuclear weapons, turning instruments of annihilation into vehicles of exploration. Project Orion conducted non-nuclear test flights of scale models at Point Loma, California, in 1959. A 1-meter model, affectionately nicknamed Hot Rod, successfully flew to an altitude of 184 feet using sequenced chemical explosions, demonstrating that the pulse propulsion concept was viable. The model landed by parachute undamaged and today resides in the collection of the Smithsonian National Air and Space Museum. However, Project Orion was ultimately cancelled in 1964, killed by a combination of political opposition. The 1963 Partial Test Ban Treaty, which prohibited nuclear explosions in the atmosphere and in space, and concerns about radioactive fallout from ground launches. The 1967 Outer Space Treaty further prohibited nuclear detonations in space. The dream of riding nuclear fireballs to the stars was put on hold indefinitely. Yet the physics remains sound. No other propulsion technology that can actually be built with existing materials and knowledge offers anything close to Orion's combination of thrust and efficiency. Every serious study of interstellar propulsion since 1960 has either been based on or inspired by the nuclear pulse concept. Today, the legacy of Project Orion lives on in ongoing research into advanced nuclear propulsion. NASA and DARPA are jointly developing the Draco program, demonstration rocket for agile cislunar operations, which aims to test a nuclear thermal rocket engine in space, potentially as early as 2027 or 2028. Unlike Orion's external nuclear detonations, a nuclear thermal rocket uses a conventional nuclear fission reactor to heat hydrogen propellant, which is then expelled through a nozzle to produce thrust. It offers roughly twice the specific impulse of the best chemical rockets, cutting Mars transit times significantly. Beyond nuclear thermal propulsion, researchers are exploring nuclear electric propulsion, which uses a reactor to generate electricity that powers ion engines, and various forms of fusion propulsion, including inertial confinement fusion drives that would use lasers or particle beams to ignite tiny pellets of fusion fuel in rapid succession, a more refined and controlled descendant of the Orion concept. These technologies represent the most promising pathways to reducing interplanetary travel times from years to months and, eventually, to making interstellar missions feasible within a human lifetime. Stepping back from the technical details, there is a philosophical dimension to this subject that deserves reflection. Nuclear explosions occupy a unique place in the human psyche. They are symbols of absolute destruction, the mushroom cloud over Hiroshima, the shadow of annihilation during the Cold War, the existential threat that still looms over civilization in the form of thousands of warheads held in readiness. For most people, nuclear is synonymous with death, and that association is not wrong. The bombings of Hiroshima and Nagasaki killed approximately 200,000 people, most of them civilians. The atmospheric testing programs of the 1950s and 1960s exposed millions of people worldwide to radioactive fallout. The arsenals maintained by the nuclear-armed states are sufficient to destroy human civilization many times over. The threat is real, it is ongoing, and it should never be minimized. But the cosmos tells a different story about explosions. The universe was born in the ultimate explosion, the Big Bang, roughly 13.8 billion years ago, an event that created all of space, time, matter, and energy in a single instant of unimaginable violence. Every atom in your body, every photon of light you see, every gravitational field you feel, originated in that primordial detonation. The expansion and cooling of the universe after the Big Bang led to the formation of hydrogen and helium gas, which eventually coalesced under gravity into the first stars. Those first stars burned bright and fast, fusing hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table until they reached iron. And then they exploded. A supernova, the explosive death of a massive star, releases approximately 10 to the 44th joules of energy in a matter of seconds. equivalent to the sun's total energy output over its entire 10 billion-year lifetime. That is roughly 10 to the 28th times more energetic than the Tsar Bomba, a factor of 10 billion. Billion. The supernova ejects the heavy elements that the star forged during its lifetime: carbon, oxygen, nitrogen, silicon, iron, gold, uranium, into the surrounding interstellar medium, where they mix with existing gas and dust to form new clouds, new stars, new planets. Every element heavier than iron in your body, including the calcium in your bones, the iron in your blood, the phosphorus in your DNA, the gold in your jewelry, was literally forged in the nuclear furnace of a dying star and scattered across space by its explosion. Without supernovae, the universe would contain nothing but hydrogen and helium and planets. Chemistry, biology, and consciousness would be impossible. Destruction and creation are, on the cosmic scale, the same process. Even black holes, those ultimate endpoints of gravitational collapse, participate in this cycle of destruction and creation. When two neutron stars collide, an event that produces a brief, intense gamma-ray burst, the collision can forge the heaviest elements, including gold and platinum, and scatter them into space. When the supermassive black hole at the center of a galaxy launches its relativistic jets, those jets can actually trigger star formation in distant gas clouds by compressing them to the point of gravitational collapse. The universe operates through a constant interplay of violent energy release and constructive reorganization. In nuclear physics, the fusion and fission of atomic nuclei is the fundamental engine driving this process at every scale, from the hearts of stars to the formation of the elements that make life possible. Humanity stands at a peculiar crossroads in this cosmic story. We have discovered the physics of nuclear energy, the same physics that powers every star and forges every element, and we have used it, first and foremost, as a weapon. We have built the capacity to destroy ourselves many times over. But we have also glimpsed the possibility of using nuclear energy to extend our reach beyond this one small planet, to power spacecraft that could carry us to Mars in weeks rather than months, to the outer solar system in years rather than decades, and perhaps, one day, to the stars themselves. The same nuclear fire that could end civilization could also be the key that unlocks the universe. The choice is ours. Whether nuclear energy remains humanity's sword of Damocles or becomes our ladder to the stars depends entirely on the wisdom, restraint, and vision of the generations to come. The physics does not care about our intentions. The atoms will fuse or split regardless of whether we aim them at a city or at the void between the stars. It is up to us to decide what we build with the fire we have stolen from the heart of the universe.